Okay, so given this, prove that. This is Q, this is P. All right? How do we go about proving that H is a group? Now we know it. We know it's a subset. Okay, that's given. So all we have to do, if given this and we have to prove that H is a subgroup of G, all we have to do is prove that H is a group with the same binary operator as G. All right? And we will use these three. And remember, we do not for the subgroup, we do not have to test for associativity. That's just inherited from the parent group. Okay? So we only have to test for these three things. But effectively, these three things are just given, right? Q is these three things. Now, so what are the three things? You have to test for closure. There has to be a unit. And there have to be inverses all in H, all in the subset H. Okay? Well, let's do those one by one. So if you have any two members of your subset H, then the product, X binary operator Y, or just shorthand XY. Now if I get rid of that. Okay, so XY belongs to H. You're given that. So for any pair, any XY belonging to your subset H, the product, X binary operator, X little circle Y, also belongs to H. So it's closed. Okay, so closure. So closure, done. Seal, closure. That's done. All right. The next thing, is there a unit? Does H, the subset, does it have a unit? Well, you're given one, right? You're just told there is one. So, okay, so the unit, there is a unit, so that's okay. And the third one, inverses. Well, Q includes that as well, because look, for all, the V with a little, the for all or for every, for every member, for every X belonging to this subset H, there is, I haven't put it here, but there is an inverse also belonging to H. Well, that means the inverses exist, right? So the inverses exist, and the fourth condition to be a group, the associativity, that's inherited from G. So we don't have to bother about that. So these three conditions are satisfied, and therefore H is a group. Okay, so we've proved it. We've proved it this way. If Q then P. All right. Now, what about the other way? Okay. So now you start with H is a subgroup. So H is a subgroup of G. Right? You assume that. This stuff all comes out almost by definition, right? If H is a subgroup, then it's closed, right? It has a unit, and it has inverses. For each element there's an inverse, and it's associative. Okay. Now, if H is a subgroup of G, it inherits G's associativity. Okay. So H is associative. Know that. So we're going through the four conditions. So H inherits G's associativity. So the associativity is okay. Now H is a group, right? It has the unit. I can draw it. So you may query, well, could H have a different unit from G? So let's, in terms of diagram, prove that that's impossible. Like, if that's the big group G, and here's the subgroup H, let's say. Now let that be your E, the unit of H. Now there's a theorem, it was the first thing we proved in group theory in the previous lecture. A group has a unique unit element, right? There's only one. Now if E is a member of H, then this unit is also the unit of G, because there can only be one. You can't have something like this. You can't have another unit F, right? Where E and F are the units of G. So E has to be the unit of G as well. Okay. So we have the unit. Now it's a subgroup. So every member of H has an inverse. Okay. So we've got that. And that's it, right? Oh, closure. Well, yeah, it's a subgroup, so it's closed. So every pair, every possible product, XY of H is closed because it's a group. It's a subgroup, but that means it's a group. So it has those four conditions. So you get this. Okay. So we have now proven Q. So if P, it's this, then Q. So that's done. Right, so that's Theorem 21. Now let's do one example before we get on to the problem-solving part of the lecture. I've learned from experience just a little bit of soap helps. But then I have to wipe it off with a towel. And for the soap to work, it has to be wet enough for that to, and then you have a drying problem. So it really is catch-22. You have to change the parameters somehow. Okay, so let's actually solve a problem. Okay, here's the exercise. You're given A and B belong to the natural numbers, belong to n. I don't know if you can see that. It's rather. If they had a hairdryer. Okay, so if A and B belong to the natural numbers, and you have a set that's defined in the following way. Oh God, I have to dry it again. For those of you who follow me for years, maybe in many lecture courses, you might look back on these initial teething problems with a mixture of frustration and humor. There has to be a better way, right? This is just a joke, a sick joke. Now, is that dry? Dry enough? Try again. So. If it's not the board, it's the pens. So A and B belong. Okay, it's starting to dry. A and B belong to the natural numbers. You have a set defined in the following way: XA plus YB such that X and Y belong to the integers. belong to the integers. I'll come back to that if I remember. Okay. Now you have to prove that H is a subgroup. I'm going to stop here, wait till it dries, and then continue.